Hello, my name is Arnaud Michel, and I'm a master's student at Queen's University in Canada. And this work is on bridging the gap between the protoplanetary and debris disks. And it was done in collaboration with Nienke van der Marel and Brenda Matthews. So we set out to answer two key questions of how do disks evolve between the protoplanetary and debris disk phases, and what mechanisms drive the dust growth and disk evolution in these later stages. And so there have been some previous studies that show a drop in the dust mass at 10 million years. In both of these plots, we have the dust mass as a function of age for the individual targets, and we can see that at 10 million years, the drop in dust mass was then used to ascribe the transition from the protoplanetary to the debris disk phases. More recently, Lovell et al. 2021 present ALMA observations of a series of possible class 3 disks in lupus, which have very low millimeter dust masses. And so from these observations, they provide conclusions which include the possible rapid planetesimal formation in lupus. And so this begs the question of how these earlier protoplanetary disks connect to these later stage debris disks. So we set out to do this with an investigation into a larger sample of class 3 disks. For our purposes, a class 3 disk is an object in a young star forming region with a low infrared excess. So across 11 low UV nearby star-forming regions of ages between 1 and 12 million years, we use Gaia-constrained YSO membership papers of the regions to construct our large YSO sample, and we combine this with infrared data. We then retrieve a full sample of about 1,000 class 3 disks, and of those, we found ALMA sub-millimeter or millimeter observations from the literature and the ALMA archive for 85 class 3 disks. So then we do a first order millimeter dust comparison of class 2 disks, 3, and debris disks. In red, in this cumulative distribution fraction plot of the dust mass divided by the stellar mass, we plot in red the lupus class 2 disk population, in orange a upper SCO class 2 disk population, followed by all the class 3 disks grouped together, and then the debris disks further in green. And so we can see the marked evolution where the millimeter dust mass decreases between region age for the same evolutionary stage, but also between evolutionary stages further on. Then instead of using age, we use the fractional disk luminosity as a proxy for evolutionary stage. This is a disk luminosity divided by the stellar luminosity, and the way by which we calculate this is from the SED plot here, where the excess infrared flux between 1.6 microns to out to 110 microns is ascribed to being the disk flux from the small micron-sized dust. And then when you divide that by the shaded red region of the stellar flux, we have this fractional disk luminosity. And so now we're plotting the millimeter dust mass as a function of fractional disk luminosity. So tracing the millimeter dust and on the x-axis, the micron-sized dusts. And first we have the lupus class 2 disks and upper SCO, and we can already see that the upper SCO disks are generally of lower millimeter dust masses. Then we can delineate which ones of these are structured, and that is transition and ring disks, which have been observed to have rings and cavities in ALMA observations. And we can see that they populate the higher mass end of these class 2 disks, being extended as well as very massive. We can then add in our class 3 disks, which emerge from the lower mass region in the class 2 phase, and then spreading out in the fractional disk luminosity regime. Later on, when we add the debris disk sample, we can see that these extend much further down into both the millimeter dust and the fractional disk luminosity. So what exactly is going on in terms of processes? And so we describe the millimeter dust drop in the class 2 disks as being radial drift and dust growth. And we, at the same time, will delineate which ones of these are most impacted. While the structured disks have gas pressure bumps and thus dust traps, they prevent efficient radial drift and thus retain high millimeter dust masses for a wide range of fractional disk luminosities. However, the remaining disks below within the class 2 phase, which we'll call radial drift dominated, do not have sufficiently large dust traps and cannot prevent the efficient radial drift from removing this millimeter dust, thus making it drop rapidly. Furthermore, in the evolution of the fractional disk luminosity parameter, we describe this as the disk dissipation of the class 2 into class 3 disks, taking place from accretion, from photoevaporation and disk winds. And so this is pushing the micron-sized dust out of the system. And so to some extent, we can see the partial independence of these two parameters, such that while radial drift can mainly occur for the radial drift dominated disks, the disk dissipation mechanisms seem to be working for even the structured disk, which have millimeter dust traps. And at the same time, we can see that the sharp transition between the class 2 and class 3 phase occurs really when the micron-sized dust becomes optically thin and further evolves. So looking at these two different populations of radial drift and structured disks, we can then hypothesize which ones can be the progenitors to debris disks. And we propose that we cannot form planetesimal belts of planetesimals at large radii from the radial drift dominated disks, because the dust is just drifted inwards and cannot remain at large radii to grow. Instead, in the structured disks, we have a phenomenon in which the dust is trapped at large radii and can grow into planetesimals, upon which eventually the gas is dissipated, and with the small dust, as seen from the fractional disk luminosity evolution, resulting in planetesimal belts that can then undergo the collisional cascade and end up as the debris disks that we see here on the right. Further evidence for this is in the transition disk fractions as a function of stellar mass. And we can see here a plot from van der Marel and Mulders in the center, where as we increase in stellar mass, the transition disk fractions reaches up to 50%. And so this bias towards higher mass stars, in that sense, joins the bias in the debris disk sample observations. And so all in all, how do we reconcile this with this age of 10 million years, and how long does a protoplanetary disk live? And so now we're going to pivot back to the small micron-sized dust as we look at the disk fraction as a function of age, seen here in the MAMAJET 2009 plot for different regions. And so the disk fraction is based on the number of class 1 and 2 objects divided by the number of class 1, 2, and 3 objects. And so this classification mechanism is based on the infrared spectral index, which relies on the micron-sized dust present. And this yields a timescale of 2.5 million years. So we've got a bit of a problem in terms of ages. And so environment matters, and we cannot forget that. And when we're looking at these disks here, what is the effect of external photoevaporation? On the right, we have again disk fraction as a function of age, and we can see the difference between the solid line, which are disks which are far from an O star, and the dotted line, the dashed line, which is disks close to an O star. And we can see a dramatic drop in the disk fraction percentages as a function of age. And so when we revise the MAMAJET 2009 plot, we find that most of these disks, most of these regions have disks that are close to OB stars, and so subject to this large external photoevaporation. This prompts us to present updated disk lifetimes for low UV nearby regions, for which we find characteristic micron dust disk lifetimes on the order of about 9 million years. And so this is significant because most of our sensitive observations are for these nearby low UV regions where we have good constraints on the accretion rate, on the millimeter dust mass, and so on. And so this leads me to my summary, where we looked at the millimeter dust evolution in class 2 disks, which is undergoing radial drift and dust growth and not disk dissipation. The fractional disk luminosity, though, traces the small dust and gas, which evolved through disk dissipation, indicating that different dust sizes could evolve by different processes. We also present two evolutionary scenarios in which structured disks could explain the observed debris disks, while the radial drift dominated disks would just become bare photospheres. And lastly, overall, in low UV environments, we find longer disk lifetimes of about 9 million years, which are consistent with gradual disk evolution and low alpha viscosities. Thank you very much for your time.